This lesson is on the second fundamental theorem of calculus, which is typically a lesson that students read into a lot more than they need to, and end up confusing themselves more than anything. So half of the class is always blown away at how easy it is, and the other half of the class is like, I think I'm doing something wrong, it seems too easy. So try not to read into it too much. It's really not that hard of a topic, and it is pretty much common sense. So if it seems too easy, that's okay. It's because it is pretty easy. It says, suppose you were asked to find the integral from 1 to x of t squared minus 4t plus 1 dt. It says, use the fundamental theorem of calculus to do so. So, great, let's do that. The integral of t squared is t cubed over 3 minus 4 t squared over 2 plus 1t. We're evaluating that from 1 to x. If I use the fundamental theorem of calculus, that's x cubed over 3 minus 2x squared plus x minus, if I plug in 1, that's 1/3 minus 2 plus 1. If I simplify that, I get x cubed over 3 minus 2x squared plus x. 1/3 minus 2 plus 1 would be 1/3 minus 1. 1/3 minus 1 is negative 2/3, and then the negative 2/3 turns into a positive 2/3. Alright, so there's my integral. Next it says, now take the derivative of your answer. Okay, let me take the derivative of this. The derivative of x cubed over 3 is 3x squared over 3. The derivative of negative 2x squared is negative 4x. The derivative of x is 1, and the derivative of 2/3 is 0. So if I simplify that a little bit, I get x squared minus 4x plus 1. It says, what is the basic result? If you haven't noticed already, the integral puts me to here, the derivative puts me back to here, which is where I started. T squared minus 4t plus 1, x squared minus 4x plus 1. So essentially it gave me back what I started with. The only difference is that it replaced all of these t's with x's, and then that's my answer. So that's about as hard as the second fundamental theorem of calculus gets. That is the second fundamental theorem of calculus. It says, if f is continuous on an open interval, then for every x in the interval, if you take the derivative of the integral, it's the same thing as the function that you started with to begin with. The only thing is that they take this x and they replace it into this t. Notice that the a value has nothing to do with it. So in this last example, the a value is 1. It didn't matter. It could have been 2 or 3 or 100 or 5,000, because all it did was create our constant of integration. And as soon as we took the derivative again, the constant of integration disappeared, and so it doesn't matter what that a value is. All that matters is that you take this x and literally just plug it into the function. So on the next couple slides, when you see me do the examples, I'm just going to draw this. I'm going to be like, oh, instead of f of t, this is going to be f of x, because that's my final answer. The only one thing that students will forget to do sometimes, and this is typically how this question appears on the AP test, is if you're taking the derivative of an integral, but instead of just a simple x up here, let's say that it's a function of x, like u. You still take that and plug it in here and get f of u, or fu. But the only difference is that you also have to multiply it times du dx. So take the derivative of whatever's up here as well. And that has to do with the chain rule. If you integrate and plug this into the function, when you take its derivative again, you'd have to use the chain rule because of that, since it's not just a simple x. And you'll see examples like that in just a second. So for this first one, it says the derivative of the integral of this. So remember, if we take the integral, which I'm not going to make you do, but if you take the integral of this and then take the derivative, it puts you back to where you started with. The only difference is that you're going to end up with an x in your answer. So the answer is the square root of x squared minus 1. Notice how this x, by the way, is just a simple variable, so that's why it's just being plugged in, and that's it. For the next one, pretty much the same thing. The only difference is that now the x is on the bottom. So let's fix that. I want to put it on the top. And so in order to do that, I'm going to flip this upside down. This is d dx negative integral from 3 to x of t sine of t dt. So my answer is negative, and again, we're just going to plug in this x into the function everywhere I see a t. So it's negative x sine of x. The 3 on the bottom has nothing to do with it. The only thing is that the x has to be on the top. For the reason that if I did actually take this integral and I used the fundamental theorem of calculus, it's f of b minus f of a. So if I plugged in 3 first and then plugged in the x and subtracted them, the 1 on the bottom ends up being negative, which is why it turns into this negative here. The last one, we have this x squared that we're going to plug in. So this is cosine of x squared. Remember, this is the one, though, where this is not just a basic simple x. So because of this, when we use the chain rule, we would have to multiply by the derivative of x squared, so times 2x. And that's our final answer. And again, I actually want to show you this one worked out a little bit more just so you can actually verify that this makes sense to you. So let me erase some of these other ones really quick. So let's do this one as if we were actually going to do it the long way. So I'm going to take the integral of this. The integral of cosine of t is sine of t. And I'm evaluating from pi over 2 to x squared. If I plug in the fundamental theorem of calculus, if I plug in x squared, sine of x squared, minus sine of pi over 2, I get sine of x squared minus sine of pi over 2 is equal to 1. And then if I take this function, that was the integral, if I take this function and actually take its derivative now, the derivative of that, the derivative of sine of x squared is a chain rule problem. So the derivative of the outside sine would be cosine of x squared, cosine of the inside, times the derivative of the inside. So times x squared's derivative would be times 2x, and the derivative of 1 is 0. So notice that I got the same thing, cosine of x squared times 2x, cosine of x squared times 2x. That's why when this is not just a simple x, you have to multiply it times the derivative of this function because of the chain rule when you take its derivative. All right, here's some ways it appears on the AP test. And again, this only works if you're taking the derivative of the integral. If it just said to take the integral, this would not work. But because these two things are inverse operations, they're undoing each other. The integral puts you back up to the original function, and the derivative takes you right back down to where you started. So I'm going to plug in x squared everywhere I see a t. So that's sine of x squared cubed. But don't forget, since this is not just a simple x, we also have to multiply it times the derivative of x squared, so times 2x. If I simplify that, I get 2x times sine of x to the 6th power, which is answer choice E, 2x sine of x to the 6th power. And that's it. Like I said, it is as simple as it seems. If it's just a simple x, literally just substitute it into the equation because the derivative and the integral are inverse operations. If it's anything other than just a simple x, substitute it into the equation and then multiply by the derivative because of the chain rule. And that's the second fundamental theorem. It's not a heavily weighted topic on the AP test. It maybe shows up once or twice, but it is an easy point if you do remember it.